Welcome back to this lecture on biochemical engineering. If you remember, what we did in the last class was essentially we were looking at multiple receptors and what happens when in the species in the complex the ligand binds to multiple receptors. We talked about the fact that these multiple receptors essentially bind independently to the ligand, and the binding of one does not influence the other. And then we said, is it possible to determine separately whether these multiple receptors, receptor 1, the amount that receptor 1 binds to the ligand, the amount that receptor 2 binds to the ligand? We said, well, it's not always easy to figure out, because what we do is we label the ligands essentially. So, the ligand, if there is one kind of ligand, it will either bind to receptor 1 or bind to receptor 2, and there is, we are just looking at the fluorescence or some kind of labeling, and it's not possible to figure out in general whether receptor 1 binds or it binds to receptor 1 or it binds to receptor 2. In some extreme cases, obviously it's possible, and what are those cases? So, the case that we talked about was when a receptor of a particular kind has a much higher binding affinity than the receptor of the other kind. And if you remember, so this was what we're doing if I go to the screen now. So, a receptor 1 and receptor 2 bind, and the steady state concentration of the complex is the amount of receptors 1 binding to the ligand plus the amount of receptor 2 binding to the ligand. So, the first term you find here, which is NC Cl0 nRT 1 over Cl0 plus Kd1, that is the amount of receptor ligands binding to receptor 1, and the second term that you see here, Cl0 nRT2 over Cl0 plus Kd2, that is the amount of ligands binding to receptor 2. So, the fact is that each of these receptors act independently and bind independently, and there is no influence of the binding of one receptor to the binding of the other. But it is possible, as I said, to distinguish between the two values if the Kd, that is the dissociation rate constant of the binding of receptor 1, is much higher or much lower than the receptor binding rate constants of the second one. Now, if you remember, so we went through the calculations, and I am not going to repeat all of that, and when we did the calculations, we took the case when the amount of complex that was there at the beginning was 0, and we did all the calculations. And what I want to attract your attention to is this fact, this biphasic nature of the curve. So, what you see over here is NC over nRT, and this is time. So, you have a single receptor, and in the case of single receptor the curve is monophasic, whereas in the case of two receptor the curve is biphasic. Now, as you can see over here, these are data here, and I am going to look at that. So, look at the Kd1, the Kd1 is 1 micromolar and the Kd2 is 100 micromolar. So, there is a 2 orders of magnitude difference between the dissociation rate constants of 1 and 2. So, if Kd1 is 100 times, so here if Kd1 is much smaller than Kd2 as the case is, then K minus 1, let us say, over K1, that is the backward rate constant over the forward rate constant, is much smaller than K minus 2 over Kd2, which means affinity of receptor 1 is much higher than affinity of receptor 2, right. So, this is what we concluded, that the affinity of receptor 1 is much higher than receptor 2 if this is the case. And these are cases when we can really distinguish between the two kinds of receptors, because as I just showed in the biphasic response that we had. So, what does this lead to if Kd1 is much smaller than Kd2? What this leads to is that in the exponential graph that you have, the slopes of the exponential graph at all points of time will be very different, and what you see is that there is a clear biphasic nature, or in other words, the slope increase in a certain way and then they decrease suddenly. So, if I can go back to the screen quickly, so you will see that this is the slope, so some kind of exponential, but this exponential, the slope of this curve, whether it is exponential or something close to linear, does not matter, is very different from the slope of the next curve. So, which means what? That if these two receptors are there and the KD1 of one is much smaller than the KD of the other, or in other words, receptor 1 has a much higher affinity than receptor 2, then this implies that whenever you let these ligands loose on the system, okay, so whenever you let these ligands loose on the system, so receptor 1 will capture these ligands. So the ligands are around, so receptor 1 will immediately come and bind with the ligand. So as a result, the initial amount of binding that will occur will essentially be because that of receptor 1. Okay. So once we understand then we realize that yes, the two slopes are very different from each other. So initially you have a much higher slope and then the slopes decrease with time. So what this implies is that for the case when the slope is higher or in the initial time period, so as soon as you let the ligands loose on the receptors, the receptor 1 is binding with the ligand. So this will essentially imply that the receptor the first slope, that is the higher slope, that corresponds to the binding of receptor 1 to the ligand. It is not that receptor 2 does not bind at all, but the fact of the matter is that much of the binding that occurs, most of the binding that occurs is because of receptor 1. And if you come to think of it, if you come to think of these two as competitive binding, that is receptor 1 is binding competitively to receptor 2, then what you realize is that because the rate constant or the affinity of receptor 1 is 100 times that of receptor 2, so the bindings would always be in the ratio, more or less in the ratio of 1:100 or 1:99. So if 100 ligands bind, 1%, only 1% of them is binding to receptor 2 and 99% of them is binding to receptor 1. So how does this help us? How does this knowledge help us? I gave you a problem at the end of the last class and I will go back to that problem. This helps us in identifying the rate constants of the system, because just as I said that when we label the ligands, there is no way for us to label the receptors, we are only labeling the ligands. So when we label the ligands, what happens is that we can only figure out that what is the total amount of complex that has been formed, and there is no way for us to separate out the receptor 1 from receptor 2 or the rate constants of receptor 1 from receptor 2, but what we essentially want to measure are the rate constants of receptor 1 and receptor 2. So how do we go about it? So what we do, we choose a ligand, we purposely choose a ligand. So think of that you are doing an experiment, and how do you go about it? So you can only label your ligands, you cannot label your receptors. So what do? You purposely choose a ligand such that it binds both to receptor 1 and receptor 2, but the binding rate constant or the KD, the dissociation rate constant, the binding affinity of the ligand for receptor 1 is much higher than the binding affinity for the ligand of the ligand for receptor 2. Okay, so that's the highlight, that's the point that you need to exploit. So once you've understood that, what you do is you essentially figure out, okay, so if one is 100 times the other, and if you let the reaction happen for a certain period of time, initially what will happen is, if the reactor 1's affinity is higher, much higher than receptor 2, what will happen is all of it will go, most of the ligands will actually go and bind with receptor 1. So that is essentially that is going to happen. Then what happens? As time progresses, receptor 1 is going to be more or less saturated, and then is when you see that bend in the curve that I showed you just now. So receptor 1 is more or less saturated. As a result, what happens is now receptor 2 starts to bind to the ligand, and this is the mechanism or the hypothesis, so to say, that is what we are going to exploit as we try and solve the problem. So let us go to the problem. So this is the problem that I gave you, and what I asked you to do is that NC equals CL0 nRT1 over CL0 over KD1 plus CL0 nRT2 over CL0 plus KD2. So let's write this. So NC equals CL0 nRT1 over CL0 plus KD1 plus CL0 nRT2 CL0 over KD2. Okay. So one of the ways of tackling this is essentially just what I said, that it's very hard to be able to figure out. So you just have one curve. Come to think of it, you just have one curve. So when you had, let's go back to this, and when you had a single receptor, this was your scattered plot, right? So when you had a single receptor, you had two unknowns. One was nRT and the other one was Kd, and you could draw a scattered plot which was linear, and from the slope you figured out nRT, Kd sorry, and from the intercept you could figure out nRT. So, two constants you needed to figure out. You had one plot, and from the slope you figured one, and from the intercept you figured another. But here what happens is the problem that I gave you, sorry, so the problem that I gave you here, the problem with this is that you have 1, 2, 3, 4. So, 4 unknowns and 1 plot. Okay. So, how do you go? So, this can at most give you 2 unknowns. So, how do you figure out the other 2 unknowns? So, what we do is we obtain a scattered plot. Okay. Now, typically a scattered plot would be linear. So, if you do NC over Cl naught over NC, then for a particular value of Cl naught equals say 1 micromolar or 10 micromolar, something like that. This is what you get. This is your plot. But in this case, what will happen is that given that Kd1 is much less than Kd2, okay, so your plot is going to be something like, let us keep this formula next to each other. Okay, so your plot is going to be something like this and this. Okay. Why is that going to be the case? The reason is that NC equals NC1 plus NC2. Okay. That is what my total. So, the complex from receptor 1 and the complex form from receptor 2. Okay. That is what it is going to be, right. So, when that is the case, then when you have a limited amount of a small amount of complex that is formed, what will happen is much of it will be from receptor 1. Is it clear? Why is that going to be from receptor 1? Because receptor 1's affinity or affinity of receptor 1 is much greater than that of receptor 2. Okay. So, that is what will happen. So, you will have most of it will be formed from receptor 1. Now, once receptor 1 is more or less saturated, most of the receptors have bound to the ligand, then only receptors 2 starts to form, right. So, then what happens is you can exploit this as receptor 1. You can call this almost as receptor 1, and this would be primarily receptor 2 plus maybe receptor 1 also. Okay. So, what we do now? So, we have our equation NC equals NC1 plus NC2, which equals Cl naught nRT1 over Cl naught plus Kd1 plus Cl naught nRT2 over Cl naught plus Kd2. Now, for the first part of the plot, so if my scattered plot is something like this, NC over Cl naught over NC, this NC that you get over here is essentially NC1, okay, this value. So, I can straight away from the, so if I take this part of the plot over here, I can straight away say that the slope of this equals, the slope of the first part equals minus 1 over Kd1 and intercept equals nRT over Kd1. Okay. I can straight away say this. So, what happens is essentially I use the first part of the slope to evaluate both my Kd1 and nRT1, and the second part I can calculate, I can assume that both receptor 1 and receptor 2 are present, and I can go ahead and calculate everything I want. Or second part, I can make an even more simplifying assumption and say that this is equivalent to NC2, in which case the slope of this will give me minus Kd 1 over minus Kd2, and the intercept will give nRT2 over Kd2. So, that is a possibility. So, I can do something like this. So, if that is the case, then slope, this is NC over Cl naught over NC, then slope equals minus 1 over Kd1, intercept equals nRT1 over Kd1, and slope here can be minus 1 over Kd2 and intercept equals nRT2 over Kd2. That is a possibility, or here you can assume both receptor 1 and receptor 2 to be acting, in which case you have to do a little more complicated calculation, but this is something you can definitely take. So, that is the way we solve this, otherwise there is no other way of looking at it. Now, let us look at some other things here, some other variations of the problem over here. As you can see, that what we are talking over here is now start to talk about here is interconverting receptor subpopulation. So, something like where the receptors convert within into each other, two different forms. So, essentially what happens is that in the previous part of the lecture, what we talked about are receptors that work completely independently of each other and they bind to the ligand independently. What we are going to talk about now are cases where the receptors bind, but they do not bind independently. Okay, they bind. There is an interdependence between these receptors, or in other words, the receptor populations are subpopulations which are interconverting to each other. And what we mean when we say they are interconverting to each other, essentially it's a morphological change. It's a conformational change that's happening in the receptor. So, it is not the chemical composition of the receptors as such that are changing, but the conformation of the conformational change occurs in the receptor. And what does the conformational change entail? It essentially means that the rate constants, the dissociation and the association constants, or in other words the binding rate constants, would change for these cases. So, let us look at this. So, interconverting receptor subpopulation. So, if you look at the screen, what happens is that often the receptor undergoes a conformational change, just as I said, after binding to the ligand. Okay. And so, when we are talking of two different receptor populations, how does this differ from what we had done before? Is that what we had done before were two completely different receptors which have affinity for the same ligand. Here is not that case, it is not two completely different receptors, but the same receptor which is undergoing conformational change, and as a result the dissociation and the association constants are differing here. So, the change however does not affect subsequent ligand receptor binding. So, but there is a conformational change that occurs, and the most general case, the receptor is present as an interconverting subpopulation. That is what we are going to talk about and model today. And so, in the most general case, the receptor is present as an interconverting subpopulation, and these subpopulations have differences in rates of dissociation and association between receptors and ligand. So, just as I said, so because of the conformational change, what results because of the conformational change is essentially the fact that these receptors have different kinetic constants. Okay. So, now let us look at the model that we have over here, the interconverting receptor subpopulation model. So, as you can see over here, this is the most general form of the model, R1 plus L. So, R1 is my receptor population 1, R2 as I said is chemically the same receptor, but just R1 with the conformational change. So, R1 plus L forms the complex C1, and R1 also forms the complex changes to R2 and forms the complex C2. So, this picture may be slightly confusing. So, what I will do is I am going to write this differently. So, R1 plus L K11, K minus 1, C1. So, R1 is essentially reacting with the ligand to form the complex C1, and R1 is going through a conformational change to form R2. Okay. And then you have R2 plus L. So, again it reacts in the similar way as R1, K22 and K minus 2 are its rate constants to form C2, and these are the complexes. This is a complex and this is a complex, and it turns out that the complexes themselves can undergo conformational change to rotate between each other. So, this is C2. And the rate constants for this are K12 and K minus 12. So, this is the set of reactions interconverting receptor interconverting receptor subpopulations. So, what is happening is that the receptor 1 is binding with ligand to form a complex, and the rate constants, forward and backward rate constants for that are k 1 1 and k minus 1. Receptor 1 is undergoing a conformational change to form R 2, and the rate constants for that are k 2 1 and k minus 2 1, and R 2 reacts with the ligand as it is to form a complex C 2, and C 2 and C 1 undergo conformational change again. So, if you look over here, go back to the screen and look over here, you find that this is the way we have represented it. This is a slightly confusing way of looking at it, and therefore, I drew it, but you can write this cyclical way. So, remember, the only thing I want to point out here that it is R 1 when I draw this line, for example, the vertical line on the left, it is only the conversion between R 1 and R 2, and L is not involved in this reaction. Okay. Now, a special case of this is what you see over here, where the receptors themselves do not change conformation, but it is the complex that changes conformation. So, R 1 reacts with the ligand to form complex C 1, and it is C 1 that changes conformation to form complex C 2, and the rate constants are k 1 1 and k minus 1 and k 1 2 and k minus 2. So, essentially what we have done is, if you take the cyclical model up here, if you cut out these two parts, these two lines over here and these two lines over here, you get R 1 plus L gives C 1 and C 1 gives C 2. So, you get this triangle over here, and that is the special case. So, what we will do now in the remaining part of this lecture is essentially look at and model these. So, what we will do is, to start with, is we will look at the special case B first, the reason being that it is easier to model. So, we will come back and look at A after that, but essentially we will look at B first. So, in B, let us look at this. So, R 1 plus L, k 1 1 is a forward rate constant, k minus 1 is a backward rate constant, and C 1 and C 2 are the complex which undergo conformational change through the rate constants k 1 2 and k minus 1 2. So, what happens when there is steady state? Okay. When there is steady state, you can relate the NC2 and NC1, that is the rate constant 1 and rate constant 2. Let me work this out for you. So, how this happens? Fine, C1, K12, K minus 1 2 and C2. So, what is, let us write all these. So, dnr1 dt, what is that equal to? That equals k minus 1 1 nc1 minus k 1 1 nr1 cl naught, right. Now, what would be my dnc1 dt? That equals, that is a little longer one. So, k 1 1 in R 1 CL naught minus k minus 1 1 N C 1 minus k 1 2 N C 1 plus k minus 1 2 N C 2. And what would be my d N C 2 dt? That simply equals k 1 2 N C 1 minus k minus 2 1 N C 2. So, at steady state, each of these would be 0. Okay. So, at steady state, each of these would be 0. So, if that is 0, then from this equation, the last equation, let us call this equation A, B and C. Okay. Then from equation C, what we find is k 1 2 N C 1 at steady state equals k minus 1 2 N C 2. Let me go through this again. So, these are my set of equations that I wrote. These are the model equations, that dynamic model. Let us forget this steady state for a minute. So, this is what I have. unsteady state model. So, NR1 is being formed because of, so the NR1 is being formed because of this reaction, and it is being destroyed or removed because of the forward reaction. NC1 is formed from this reaction as well as this reaction, and it is also removed because of this reaction as well as this reaction. So, 4 terms here, and whereas C2 is formed in the forward direction and destroyed or removed in the backward direction. At steady state, all these 3 have to be 0. So, what we do, we first equate the simplest one, the second one to be equal to 0. Okay. So, this is what we get. So, what we immediately get is that NC2 equals K12 over K minus 12 times NC1, or in other words, if KD12 is written as K minus 12 over K12, then this is written as NC1 over KD1. Okay. So, that is what I get. Now, what is my NC? NC would be NC1 plus NC2, right, which means that NC1 plus NC1 over KD1, that equals NC1 plus 1 over KD1. Fine. Now, what is my NRT? NRT is the total amount of receptors, which is NR1 plus NC1 plus NC2, or in other words, receptors that are completely free, okay, and receptors that are in complex 1 and receptors that are as complex 2. So, this I can write now as NR1 plus, I have already calculated what my NC1 and NC2 together is, which is NC1 plus 1 over KD1. Okay. So, now if I go back to my equation over here, okay, if I go back to my equation over here, so this has to be 0 at steady state also, this has to be 0. So, what we can do is, if I equate this to 0, I get a relationship between NR1 and NC1 straight away. Okay. Let us do that. So, equating A to 0, so A is this equation out here. Okay. So, A is this equation, I am equating this to 0, which means that K minus 1 NC1 equals K11 NR1 CL0. Okay. So, NC1 equals K11 over K minus 1 NR1 CL0. Okay. Fine. So, this is what I get. So, NR1 equals K minus 11 over K11 times 1 over CL0 times NC1 over CL0. So, this I can write as KD11. Okay. Previously I had written KD12, so I can use this for KD11. So, CL0. Fine. So, this is 1. So, NR1 equals KD1, NR1 equals, let me just put it over here like this. Yeah. So, NR1 equals KD1 NC1 over CL0 and NC2 equals NC1 over KD1. Now, what was my constraint equation? My constraint equation was that NRT simply equals NR1 plus NC1 plus NC2, or I had written this as NR1 plus NC1 times 1 over KD1. Now, NR1 I can write now from the previous equation, I can write it as NR1 NC1 over CL0 plus NC1 over 1 over KD1, KD12, sorry, this is KD12. Okay. So, now I can write this as NC1 KD11 over CL0 plus 1 over KD11 12, right. So, this is what I get. So, this is my relationship between NC1 and nRT. Okay. So, nRT times CL naught, if I write, then it will be NC1 KD 11 plus CL naught times 1 over KD 12. So, this is a relationship I have between these. So, NC equals NC1 plus NC2, okay, which I have written it previously, if you remember, as NC1 over 1 over KD12. Now, NC1 I can now write as nRT over times CL naught divided by KD11 plus CL naught 1 plus KD12, okay, times this factor over here, which is 1 over KD12. So, this is my relationship that I have between these numbers. So, I can, one of the things I can do is try and convert this into a slightly more handleable form, which is k d12 plus 1 and divide this by k d11 k d12 plus CL naught 1 plus k d12. I can write it like this, or I can make it even simpler and write this as nRT CL naught divided by KD 11 KD 12 plus CL naught, divide this by 1 plus KD 12. Okay. So, this is my final relationship between NC and nRT. So, if I want to draw my Sketchet plot, which will be NC over CL naught, that would simply be equal to nRT divided by CL naught plus KD 11 KD 12 divided by 1 plus KD 12. So, I can draw a plot like this. So, if I now go back to the screen, this is exactly what we derived. NC equals NC over CL naught equals nRT divided by CL naught over KD 11 times KD 12 divided by 1 plus KD 12. Okay. So, this is the plot that I want to obtain. So, why did I do it this way? Why did I club it this way? Because if I am to draw a plot of NC, so what do? I can write this as KD apparent, okay, my apparent rate constant I can write. So, if you look at this, it even has the units of rate constant correctly. So, I can write this as KD apparent, which is KD 11 times KD 12 divided by KD 12. So, what will happen is, if I can now write my plot as NC over CL naught equals nRT over CL naught plus KD apparent. Okay. So, what I can do is, if I take a if I can either do it this way, which is CL naught over NC equals CL naught over nRT plus KD apparent over nRT, where KD apparent is this number, which is KD 11 times KD 12 divided by KD 12 plus 1, fine. This is my number. So, what I can do over here is, if I draw a plot of CL naught over NC versus CL naught, what do I get? I just get a straight line, something like this. I just get a straight line, something like this, and the slope of the straight line is 1 over nRT, whereas the intercept is Kd apparent over nRT. So, what I can straight away do is from the slope I can calculate my nRT, and from the intercept I can calculate my Kd apparent. So, what was the whole idea of this entire process was to be able to, we had plenty of constants out there, Kd11, Kd12 and Cl0, and Cl0 is not a constant, but it is something that we can vary, but nRT. So, what was the idea was to club these 3 constants that we had into 2, because 2 is something very measurable, and write the equation in such a way that we can plot it very easily. So, what we managed to do was write the equation in a way where it is a straight line, and we could just get the nRT from the intercept and Kd, and just get the nRT from the slope and the Kd apparent from the intercept. So, that was what we are trying to do. So, this is a special case, the case where the receptors themselves are not interconverting, but the complexes are interconverting. So, what about the more complex case now, and as I just said that this set of reactions could be replaced by this set of reactions, are actually written by this set of reactions, and what do we do? You know, how can we look at this and model this now? This is a slightly more complicated one. The process that we are going to do, and I probably am not going to have the time to work out the whole thing, but we will start to work out, and the process that we are going to do is exactly the same process. So, this is my these are my sets of reactions, and all we have to do, we have to write balances for each of these R1, R2, C1, C2, and let us try and do that to start with. Okay. So, R1, the balance from for R1. So, just for a second I will keep this out here, so that you can write these set of reactions down. So, R1 plus L K1 forward reaction K11 backward K minus 1 gives C1, R1 forward reaction K21 and K minus 21 gives R2, R2 plus L forward reaction K22 backward K minus 22 gives C2, and C1 forward reaction K12 backward reaction K minus 12 gives C2. Okay. So, let us write the balances for R1 now first. So, R1 is being formed by this reaction K minus 11 NC1 and is being removed or being depleted by this reaction NR1 times Cl0, and for another set of reactions, and for that R1 is being formed from K minus 21 NR2 and being depleted from K minus K21 NR1. Okay. Similarly, NR2 dt is being formed from K minus 22 times NC2 and depleted from K22 NR2 times Cl0, and there is the other interconverting reaction, which is it's being formed from K21 NR1 and depleted from K minus 21 NR2. Okay. And what about C1 and C2? That also you have 2 sets of reactions. So, this is the set of reactions for NR1 and NR2, and if we look at C1 and C2, so dNC1 dt equals K11 NR1 Cl0 minus K minus 11 NC1, okay. And then you have K minus 12 NC2 minus K12 NC1, and similarly we can write the balance for C2, which is K 22 NR2 Cl0 minus K minus 22 NC2 plus K 12 NC1 minus K minus 12 NC2. So, these are my 4 balance equations that I write, and what do I do with them? So, at steady state I have to equate all of these to be equal to 0. Okay. So, let us look at the total amount of complex that we have. So, this is my set of equations for NC1. So, let us look at the total amount of complex that we have, which is NC1 plus NC2. What is that number? If I add all the terms that I get over here, I get K11 NR1 Cl0 minus K minus 11 NC1 plus K22 NR2 Cl0 minus K minus 2 NC2. Okay. And for NR1 and NR2, if I add the two equations NR1 plus NR2, just this is not basically these are adding these two equations. So, this is at steady state, this is basically this is ddt of this. At steady state this equals 0. Similarly, ddt of NR1 plus NR2 equals K minus 1 minus 11 NC1 minus K11 NR1 Cl0 plus K minus 22 NC2 NR2 NC2 minus K22 NR2 Cl0. So, this is what we get. So, and this equals 0 at steady state. So, what we have to do essentially is that it is a little more cumbersome process. So, what we have to do essentially is that we have to solve for NR1, NR2 and let us say NC2 in terms of NC1, in terms of NC1, let us say something like that. So, when we do that, then what we can do from here, what we can get from here is that we can replace everything in terms of NC1. Now, what was my constraint equation? If you look at these two sets of reactions that I have written over here, this is, let us go one by one. So, this is NR1 and NR2 and this is NC1 and NC2. If you add all these 4 sets of reactions, what do I get? If I add all these 4, what I get is ddt, if you look at these equations, of NR1 plus NR2 plus NC1 plus NC2, the summation is ddt of that, the summation is 0, okay, which means that NR1 plus NR2, this implies that NR1 plus NR2 plus NC1 plus NC2, their sum come out to be a constant, which is NRT, that is the total amount of receptors present, or in other words the total amount of receptors that was present is divided into the receptor 1 that is free, receptor 2 that is free, receptor 1 complex that has been formed and receptor 2 complex that has been formed. Okay. So, we go through these calculations and I am skipping the details of the calculations because we do not really have a lot of time. So, once we go through these calculations, if you look at the screen, what you find over here is that this constraint equation that I wrote. So, what you need to do, you have to keep substituting everything. So, you decide that you want to substitute everything in terms of say NC1. So, you convert NRT1 as write it as in terms of NC1, substitute here, convert NRT2 and write it in terms of NC2 and substitute here, and NC1 sorry and substitute here, and write NC2 also in terms of NC1 and substitute over here. So, once you do all that, what you will find is just like in the previous case, just like in case B as we did, case B we did explicitly, and here also you will find just like in case B that NC could be written as Cl0 NRT over Cl0 plus Kd apparent. Okay. So, this is what you can write. So, NC over Cl0 is NRT over Cl0 plus Kd apparent, where Kd apparent is slightly more complicated over here. It is Kd 11 times 1 plus Kd 1 over Kd 21 over 1 plus Kd 12, which could also be written as Kd 22 times 1 plus Kd 21 over 1 plus Kd 12. Okay. and all these numbers are written over here. So, Kd11 is the dissociation rate constant for the first case here, that is Kd minus 11 over Kd11. Kd21 is Kd minus 21 over Kd21, or in other words the dissociation rate constant over here between the two receptor subpopulations. So, this is the way the receptors are changing conformation. Kd12 equals Kd minus 12 over Kd12, which is how the complexes are changing conformation, and that is the dissociation rate constant for that. And Kd22 equals minus Kd22 over minus K22 over K22. Okay. So, this is how the second receptor is binding to the complex. So, this is the thing. Now, what happens is, what you had been able to do, or we had been able to do through this process, is we had these 1, 2, 3, 4 constants and nRT, of course, the fifth constant. So, we have been able to reduce these 5 constants into 2, or in other words Kd apparent, if you look at it, involves all these constants. So, what we had been able to do in the process is we had been able to reduce these 4 constants into a single constant, Kd apparent. And why did we do that? The reason is again the same reason that we had before, which is that it is very hard to be able to handle all of these. So, what we essentially have is just one equation over here. So, Nc equals Nc1 plus Nc2 equals Cl naught nRT over Cl naught plus Kd apparent. Okay. So, this is my equation. So, the advantage is Nc over Cl naught equals nRT over Cl naught plus Kd apparent. Fine. So, Cl naught over Nc equals Cl naught over nRT plus K apparent over nRT. So, what do? You take different values of Cl naught, label the ligands, and you perform your experiments for each of these sets, and then you find out that what you essentially what is the ratio of Cl naught over Nc for each of these sets, and measure it in terms of Cl naught. So, essentially this is your, if you want to plot it over here, this is your plot. So, Cl naught over Nc, and this is Cl naught. So, just as I said that this is going to be a straight line over here, and the slope is going to be equal to 1 over nRT, and the intercept is going to be Kd apparent over nRT. Okay. So, this is essentially what we get, and Kd apparent over here equals Kd11 over 1 plus slightly complicated formula, 1 plus Kd12 divided by 1 plus Kd21 right here, and divided by Kd12. So, this is my formula. So, what we essentially do, we conduct experiments with taking different amounts of ligands and figure out how much is my total fluorescence that I get, that is the total amount of complexes that have been formed, and we measure that and plot it against the amount of ligands that are there. So, in case 2, case 1, this is case 1, and case 2 we did separately, but if we have been able to do case 1, which is a lot more complicated case than case 2, then case 2 would be a natural fallout of case 1, and it would come as 1 over when the case for the case that 1 over Kd21 is 0, or this case, that is 1 over Kd21 is 0, or in other words Kd21 is much greater than Kd minus 21. Okay. That is, or in this case, this step is not there. So, if you go to case B, you will see that what is case B? Case B is when the receptor populations themselves are not interconverting, but it is the complexes that are interconverting. And when does that happen? When there is no direct interconversion between the receptors. So, if you look here, so what we are doing here is that there is this reaction between the receptor interconversion, and that reaction has to be absent. Okay. So, I think we more or less looked at different cases over here, and what you see on the screen right now is a summary of the different processes that we looked at. So, if you remember, so this is I will run you through very quickly. So, we started with a single receptor case, and let me go through this very quickly and try and summarize what we have done in the last few cases. So, remember this was a very important plot that we looked at. Just a second. So, this is where we started with. This is a single receptor ligand binding case, whether it is a receptor binding to a single receptor binding to a single ligand, and we assume that there is no receptor depletion out here. So, we got straight linear scattered plots and stuff like that, and then we started to look at. So, this was the simplest case possible, and for this case the scattered plot is linear, is a straight line. Okay, the scattered plot is essentially the important plot that we will keep looking at here, and NC over CL naught versus CL naught, and we said that this is linear. But then we said that there could be different deviations from this, and what we have been studying in the last few lectures are these deviations from the scattered plot. So, the scattered plot is linear if the receptor, if the ligand is present is in excess and the receptor binds in a simple bimolecular kinetics. Now, when the receptor deviates from these, you have what is known as positive cooperativity and negative cooperativity. Okay, and that is what we looked at. So, you look at the scattered plot over here, and there is negative cooperativity and positive cooperativity, and let me. So, these are the different cases that we looked at, different deviations. The first one we looked at is ligand depletion. So, Cl was no longer Cl naught, it became a quadratic equation, we solved it and we showed how to do that. Next was multiple receptors binding, and what was the difference between what is the point about multiple receptors? They were binding independently of each other. So, two different receptors binding to the same ligand, but binding independently of each other. And then we looked at cases where there are not actually multiple receptors, but the receptors were changing conformations, as a result of which their rate constants were changing, and they were essentially behaving like multiple receptors. So, here is a summary of everything that we did in the last few lectures. So, single receptor, when we have a single receptor, the scattered plot is linear and the dissociation kinetics is single exponential, as it is written on in the table out here. When you have a single receptor, but ligand is depleting, then the scattered plot is nonlinear and the dissociation kinetics is still single exponential. Now, is the interesting case of two different receptor populations, and the scattered plot is nonlinear and the dissociation kinetics is double exponential, and we discussed this at the beginning of this class, that if the dissociation constant of one is very different, is very large as compared to the dissociation constant of the other, we are in business and we can separate out the rate constant, the dissociation and dissociation rate constants of the two cases, otherwise it is very hard. Next, we looked at the case for receptor ligand interconversion, and the scattered plot is still linear as we just showed, and the dissociation kinetics is 2 or more exponential, and this interconversion is what kind of interconversion? The receptor itself, receptor subpopulation itself changes conformation, becomes another receptor. So, because both these are chemically the same, they both bind to the same ligand, but the dissociation rate constants are different and they form different complexes which can also interchange, that is interconvert through change of conformation. And then there are other cases which we did not really study, but these cases I just want to go through quickly. One is interconversion of ligand to a non-dissociable form, and in this case the scattered plot is linear and the dissociation kinetics is double exponential, as you see over here. So, interconversion of ligand to a non-dissociable form, and then there is true cooperativity, in which case the scattered plot is non-linear and the dissociation kinetics is double exponential. So, let me go and show you this over here, what we had before here. So, this multivalent ligand, and these cases were receptor aggregation. So, these are other cases that can happen, that is one ligand is binding to two receptors, that is a straightforward case, but a little more complex case is the case of receptor aggregation, which is that two receptors R plus R together form an aggregate, and then this binds step by step with a ligand. So, essentially you form LRRL, which is two receptors binding to two ligands, but they bind as an aggregate, which means that two receptors bind to one ligand first, and then this ligand with the two receptor binds to the second ligand to form LRRL. So, again the kinetics is here going to be a little different. The reason this is going to be a little different is that the kinetics is going to be a little different is because the dissociation and the association rate constants are varied over here, and this is a case of cooperativity. And if you remember at the beginning of this course of this chapter, I gave you the example of hemoglobin molecules, 4 hemoglobin molecules binding to oxygen step by step, and this is a very parallel example of that. So, two receptors binding to one ligand first, and then the two receptor one ligand complex binding to the second ligand and forming two receptor two ligand complex. So, there is a cooperativity out here and there is positive cooperativity. This is similar to the hemoglobin oxygen binding, and then what will happen is the rate constants will be different at each of these steps, and there will be different. So, 2 receptor binding to 2 ligand is different from the rate simple case of 1 receptor binding to the rate constants will be different from 1 receptor to binding to 1 ligand. So, these are the different kinds of receptor ligand bindings that we talked of, the kinetics of this. Now, where do these kinetics come into play? What are the real physical processes where these kinetics are very important? And I had talked a little bit about this, and the one particular case that we are going to look at, and we are going to look at with respect to a particular disease, which is familial hypercholesterolemia in the following lecture, is receptor mediated endocytosis. So, receptor mediated endocytosis is a very important process, and it is very important for several biological and physiological processes, and this is where the kinetics come in. And the disease that we are going to talk about, familial hypercholesterolemia, is a genetic disorder, and we are going to look at why this genetic disorder happens. Is it because of some kinetic disabilities, that is, some kinetic rate constants is lower than what they should have been, and or some other reasons, the complex is not being formed properly, or not enough ligands, or not enough receptors. What is the reason? So, this is a very practical and interesting example and application of this theoretical study of receptor ligand binding. So, we did a purely theoretical study till here of receptor ligand binding, but we are going to apply it in the following lecture to different diseases, and the main thing that we are going to focus on is a process called receptor mediated endocytosis. With that, I will stop today, and we will talk about receptor mediated endocytosis in the following lecture. Thank you.